Hi everyone. So today we'll be looking into the parabolic PDEs, in which we'll first start with how to identify a particular given PDE is a parabolic PDE. Then we'll look for why is it called parabolic, and then how to identify this class. After identifying a particular PDE as a parabolic PDE, then we'll see what is the nature of this PDEs, how the uh, how the solution evolves over time and all those things. And then finally, we'll see some numerical methods which are used to solve this parabolic PDEs. So firstly, we'll start with like how this parabolic PDEs can be identified over along other PDEs. So to start with, a general second order PDE would be of the form of a del square u by del x square plus 2b del square u by del x del y and c del square u by del y square and the other linear terms which are there with it. So to identify whether this a particular given PDE falls in the category of parabolic PDE, what we do is we take an discriminant of this particular second order equation. So if we take the discriminant will be equals to b square minus ac. So so to classify it as a parabolic PDE, this discriminant has to be zero. So if we see for an example, if we see an example, which is basically an heat equation, which is du by dt is equals to alpha d square u by dx square. In this particular case, if you see here, the value of this is a linear term or a first order term. So this is equal. So this won't come into the picture. While if you see this is a second order term, and this second order term is of the form of this a. So here, if we take the coefficients of this particular thing, so in this particular case, b is equals to 0. Here also here we have a as alpha, and while c is also equals to 0. So if we calculate the discriminant, we get it as 0 square minus alpha into 0. So this essentially comes out to be 0. So the class of equations or the PDEs which have this particular discriminant as 0 are said to be parabolic equations, parabolic PDEs. And once we know that like this is like a particular PDE identifies as a parabolic PDE, then we can go and look into like what is the nature of this PDEs. So before going into the nature, like a thing here, like why these particular set of equations are called parabolic, that is because of the mathematical characteristics of these parabolic PDEs, such as first thing, if we see the quadratic equations, in that also the solutions which have discriminant as 0, they have a parabolic behavior, and also behavior of the solution. So basically basically have geometrical analogies to parabola. So this connection is seen in the solution properties such as the smooth and diffusive nature of things, so how things diffuse over time. And so this also comes, which is like basically reminiscent of the smooth curve of parabola. So that's why this set of equations are called parabolic set of equations. So now moving further, we will see why this nature of like what are the characteristics of these parabolic PDEs. So first thing is they are time dependent. So here we have a time dependent term, which is basically a partial derivative of any given variable over time. So the dependent variable over time. So this particular PDEs, they have time dependency, and they because of this time dependencies they need initial conditions. So initial conditions are basically at if the simulation starts from time t equals to 0, so at time t equals to 0, what was the state of the dependent variable, So this initial conditions are needed to solve this particular PDEs, and boundary conditions they follow because of this because of the spatial term which is there in the PDE. And then also, the nature of these PDEs are basically they are diffusive in nature. So diffusive means basically if there is some property which is propagating over space and time, then it over a period of time it smoothens up across the whole space. So this is the diffusive property of this. So this particular PDEs they are used to model the diffusive and smoothing phenomena of different variables. So that's why there's use of diffusion and smoothing. And then there is uniqueness and stability of this particular solution. So in this case, what happens is any small change in the initial conditions won't have a drastic impact on the output of the solution, which is over time because it is diffusive in nature. So any small change in the initial condition, it evens out or smooths out over a period of time and also over the whole space. So they are kind of stable solutions. And then this particular set of PDs, like we have discussed, they need both boundary condition and initial conditions. So this is one of the things. And applications of this PDs can be seen in like different things. So wherever we see the diffusive nature of things. So in heat transfer, temperature is one such property where it diffuses over time and space. So heat transfer applications, you can model them with this particular parabolic PDEs. Also, population dynamics can be modeled. Similarly, pollutant dispersion. So, if some factory or some particular outlet is letting some pollutant out into the space, so it diffuses over time, and the changes of that particular thing are means like if there are small amounts of this pollutants being let out into the space, so you don't see a much of difference in the whole thing because they diffuse over time and they are propagated over space as well. Similarly, in finance, small change in some stocks or something, how they affect the market, this particular thing can be modeled using this parabolic PDEs. Then we move, then we go in, we look into solving of this parabolic PDEs. So usually parabolic PDEs are solved using finite difference method and finite element methods. Here we'll be discussing about some finite difference methods. So, and there are also like two things in this particular parabolic PDEs, which are basically if we have a PDE and it has both the space terms and the time terms, then they are called as uh, this particular like set of equations which have both, they are called as this system which consists both of them, they are distributed systems. While a system in which we only have the temporal part of it and the spatial part of it is averaged along the whole space, so that we lose out on that spatial distribution, and we consider the spatial distribution to be having just an average value over the whole space. So those kind of models are called at lumped system models. And then eventually this both models they are basically simplified in such a way that using a numerical method we simplify such that they turn into algebraic equations, and then we solve this algebraic equation using some linear algebra and other techniques to solve them. So looking into this same thing, there are like three methods which are very well known. So basic first one is the explicit method. In case of explicit method, what we do is here we are considering the same heat equation. In this, if we discretize this over both space and time, so here this is the discretization over time, and if we discretize it over time, here we see that these terms are n plus 1 basically shows for the next time step, and u of n shows for the current time step which we are at. And similarly here I plus 1 and I minus 1 show the points which are spatially there. I is the point for which we are calculating. I plus 1 is the point which is ahead of that point in space, while I minus 1 is the point which is behind that point in the spatial domain. So, and alpha is the diffusion constant here. So, if we explicitly try to discretize this particular equation, then we get something of the form. This is the form, and this is so the pros of this particular method are this is very simple to implement, and in this particular case, this R is called as CFL constant, which is basically delta. Sorry, this is basically alpha delta t by delta x square. This also defines the stability of the problem. But and with this, because this particular thing has depends on the stability constant. So here, what we have is the delta t. It should maintain a ratio, which is the CFL condition. T should be less than equal to delta x square by 2 alpha. So this defines the stability of this particular problem. But the issue with this thing is, as we increase as we increase the not increase, as we decrease the spatial domain, like the points are very closer, delta x is small, then this we have in condition we have this condition which basically constrains the delta t as well. So this particular ratio should be satisfied. Then we move on to implicit methods. In case of implicit method, we consider the same equation, and in this we try to discretize this in an implicit form. So in this particular case, we have this in implicit form. This is backward Euler, and this we particularly solve it for the next time step, which basically comes out to be 2i plus 1 n plus 1 minus 2ui, then again n plus 1 plus I minus 1 n plus 1 by delta x square. So this is the discretization based on implicit formulation of things. And if we try to if we rearrange the things, this comes out of the form which is this delta t by delta x square in u minus 1 n plus 1 plus 2 alpha delta t. This basically is equals to the value of value of this variable at the given time and the given point, so spatially and locally. So this basically gives us an matrix to solve, which is of the form ax equals to b. And this is if we try to arrange this over the whole space, so for I plus 1 and all the points over the space, so this is of the this matrix particularly has this property of tridiagonal nature. So this is of tridiagonal nature, and then further this can be solved using some linear algebra methods. So some linear solvers can be used to find the variable solution at all the points. So the pro of this particular method is that this is unconditionally stable. So you can use however large time steps you want, but the solution will still be stable. And but the disadvantage of this particular method is that it is computationally very demanding, as we need to solve these linear equations for each time step. So for each time step, we'll have a new set of linear equation, which is like ax equals to b. And then we'll have to solve this for each time step. That's why this becomes computationally challenging. So, in order to find middle grounds from this two methods, which have their own pros and cons, so we can find the middle ground by doing so, which is called as Crank-Nicolson method. In this particular, this is also named as semi-implicit method. And if we try to combine the both of this, so the discretization in this case is basically 2n plus 1i. So the temporal thing remains the same. You discretize this in time, while discretizing the other domain, the spatial domain. What we do is we have a parameter which has some which has a control over this thing. We can have both the methods here. So basically discretizing it with respect to the implicit and explicit method. So this is the explicit formulation or the discretization of thing. So, and the second part is basically the uh, other part of it. So this will be ui plus 1. And so here, basically this theta parameter, controls the this controls the amount of implicitness or explicitness to be allowed. So basically, if here you set this theta equals to 0, then what happens is this terms goes out to 0, and this completely becomes explicit. While if you keep theta as 1, then what you get is this particular thing becomes implicit. And yeah, in case of this Crank-Nicolson method, where theta is chosen to be 1 by 2, this is Crank-Nicolson. The formulation for this particular thing comes out to be 2i n plus 1. This comes out to be of the form of this form. And then, so basically, the pro of this particular method is that this is second order accurate in both space and time, and also is stable. So we get both the things here. We get the stability, and we also get second order. We also get second order accurate in both space and time. While in the above methods, we only were getting second order accurate in time. So in space, sorry. And then but the only con of this particular thing is like the implicit method, it also requires solving of this linear system at each time step. So for this particular thing also, we'll have to solve the linear equations at each time step. So the number of time steps you have, or the delta, depending on the delta t and the total time duration, you'll have to solve the particular thing for those many number of times, and each time step will involve the solving of this linear equations using some linear system of equations or some linear solvers. So that's it for today. Thank you.